What if I told you a building doesn't collapse the moment one beam fails? What if the structure can think, adapt, and survive, just like a living system? Now, a real-world warning. Ronan Point, UK, 1968. A small gas explosion removed one panel. There was no alternate load path, no redistribution, no redundancy. An entire corner of the building collapsed. That's why icons like Taipei 101 in Taiwan and Burj Khalifa in Dubai don't rely on strength alone. They rely on something smarter. They are designed with massive redundancy, so local failure doesn't become global collapse. That hidden survival mechanism is called load redistribution. Welcome to StructTuts, where structures speak and engineers listen. Let's close this concept by breaking it into 7 chapters. Chapter 1. Introduction. Load redistribution. Imagine a group project. One teammate is overloaded and the others step in to help. Buildings do the exact same thing. Load redistribution is the reallocation of internal forces within a structure, without changing the external loads. It happens due to cracking, yielding, stiffness changes, or support movement. But here's the key rule. Redistribution is only possible in indeterminate structures. No redundancy, no second chance. Chapter 2. Why redistribution happens. In real structures, redistribution is unavoidable. Concrete cracks, stiffness reduces. Steel yields, stress stays constant, strain increases. Supports settle, force paths change. Construction errors, misalignment, eccentricity. Long-term effects, creep, shrinkage, temperature. And post-tensioning losses. Structures are not static machines. They evolve with time. Chapter 3. Examples. Picture a 3-span continuous beam under uniform load. The middle span takes maximum moment. Cracks form. Stiffness reduces. Load shifts to adjacent spans. Support reactions change. This is redistribution in action. The beam doesn't fail. It adapts. Chapter 4. Determinate versus indeterminate structures. Now let's compare. Case 1. A simply supported beam. 2 supports. 1 failure, total collapse. Case 2. A continuous beam. 1 support weakens. Moments shift. Reactions change. The structure survives. More redundancy, more safety. Now, let's talk about something every structure falls into. Determinate structures and indeterminate structures. First, determinate structures. These are structures where all internal forces, bending moment, shear, axial force, can be found using equilibrium equations alone. Sum of forces equals 0. Sum of moments equals 0. That's it. No extra equations, no backup paths. And that leads to one critical truth. Determinate structures have no redundancy. If one member fails, the load has nowhere else to go. Think of it like a single pillar holding a roof. The pillar cracks, the roof comes down. No warning, no redistribution, no second chance. Now, Indeterminate structures. These structures have more unknown forces than the number of equilibrium equations. So equilibrium alone is not enough. To solve them, we need more tools. Compatibility conditions, deformation relationships, and advanced methods. Moment distribution, matrix method, finite element method. But here's the payoff. Indeterminate structures have redundancy. When one member weakens, other members step in. Think of a building frame like a team. One column struggles. Beams and slabs share the load. The building doesn't collapse. It adapts. That's why most real buildings are indeterminate. Because safety is not about strength alone, it's about alternate load paths. Now, in buildings, we don't just label structures as determinate or indeterminate. We actually calculate the degree of indeterminacy. For individual elements, beams, columns, slabs, trusses, foundations, and structural systems. This tells us how many extra force paths exist, how much redistribution is possible, and how the structure will behave after cracking or yielding. We move from concepts to calculation. Let's begin with beams. For beams, we first identify whether a beam is statically determinate or statically indeterminate. We do this by finding the degree of indeterminacy. The formula is simple. Degree of indeterminacy, D equals R minus E, where R is the total number of unknown reaction components coming from supports, and E is the number of independent equilibrium equations. In two-dimensional structures, we have three equilibrium equations: sum of horizontal forces, sum of vertical forces, and sum of moments. In three-dimensional structures, we have 6 equilibrium equations. Now, the interpretation is very important. If the degree of indeterminacy is 0, the beam is statically determinate. If the value is greater than 0, the beam is statically indeterminate. And if the value is less than 0, the structure is unstable. We have example calculations shown here for different beams. Let's understand this with an example. Consider a simply supported beam. It has 1 horizontal reaction and 2 vertical reactions. So the total number of reactions, R, is 3. In 2 dimensions, the number of equilibrium equations, E, is also 3, 0. So this beam is statically determinate. In the same way, we perform calculations for other beam types. Trusses. For trusses, we determine whether a truss is statically determinate, indeterminate, or unstable by using a member-joint relationship. The governing formula is degree of indeterminacy, D equals M plus R minus 2J, where M is the number of members, R is the number of reaction components, and J is the number of joints. If the value of D is 0, the truss is statically determinate. If D is greater than 0, the truss is statically indeterminate. And if D is less than 0, the truss is unstable. For example, a simple triangular truss with 3 joints, 3 members, and 3 reactions. Substituting values, 3 plus 3 minus 6. The degree of indeterminacy is 0. so the truss is determinate. In the same way, we analyze redundant trusses and identify additional load paths. Slabs. For slabs, the determinacy depends mainly on support conditions and load distribution. Most slabs are structurally indeterminate because loads are shared in more than one direction. For example, a one-way slab behaves similar to a beam. Load transfer is mainly in one direction. A two-way slab distributes load in both directions, which automatically introduces redundancy. Because of this, slabs are usually analyzed using compatibility and deformation methods, not equilibrium alone. So in practice, most slabs are indeterminate systems. Columns. For columns, determinacy depends on end conditions and frame connectivity. A column with pinned ends and isolated loading can be statically determinate. But columns in real buildings are connected to beams and slabs and participate in frame action. This introduces additional restraints and additional unknown forces. As a result, most building columns are statically indeterminate. This indeterminacy allows moment redistribution and load sharing between members. Frames. For frames, static indeterminacy is the default condition. Frames consist of beams and columns rigidly connected. These rigid connections introduce additional moment restraints, so the number of unknown forces exceeds the number of equilibrium equations. Because of this, frames must be analyzed using moment distribution, matrix methods, or finite element analysis. This redundancy is what allows frames to survive local failures. Foundations. For foundations, determinacy depends on soil interaction and continuity. An isolated footing can behave close to determinate, but combined footings and raft foundations are highly indeterminate systems. This is because soil pressure is not uniform and settlement is not equal. So load redistribution occurs through the foundation system, which makes foundation design both structural and geotechnical. Walls. For structural walls, determinacy depends on continuity and boundary conditions. Load-bearing walls in isolation can be determinate. But in real buildings, walls interact with slabs, beams, and frames. This interaction introduces additional force paths. So most structural walls are statically indeterminate. This allows walls to redistribute load during cracking or settlement. Chapter 5. How steel enables redistribution. Concrete cracks. Concrete is brittle, but steel saves the day. After yielding, steel stretches without gaining stress. That extra deformation gives the structure time to adapt. Plastic hinges form, the structure becomes determinate, and forces redistribute. Chapter 6. Site relevance for engineers. On site, redistribution is happening, whether you like it or not. Site engineers must watch cracks and deflections, identify critical members, use shoring or jacking intelligently, redesign force paths, not just add steel. Blind overdesign is dangerous. Smart redesign beats more steel. Chapter 7. Codes and practical design rules. All major codes allow redistribution, but with discipline. Under reinforced sections, proper anchorage and curtailment, ductile detailing. Analysis alone doesn't save buildings. Detailing does. At the end of the day, more steel does not automatically mean more safety. Without ductile detailing, without proper continuity, and without understanding load paths, adding more steel won't save a structure. Smart design is always better than over-design.